Alex is the, have you graduated?
Yeah.
Oh, so it's Dr. Alex Chen, so he's going to be talking, as I said, about LED cooling.
All right, thank you, Gaiman. So as Stephen mentioned earlier, with building efficiencies, there are multiple ways you can sort of attack this problem. There's heating and lighting being the main thing. So looking at lighting, there's a lot of push now towards moving to LEDs because of their efficiency and longevity. However, one of the issues with LEDs is the heating problem. About 60% of the energy that's inputted into LEDs ends up wasted as heat. And as the temperature of the LED junction increases, you end up having issues of the intensity that you can run these lighting solutions, and of course the longevity of that. So what we've been tasked to do is to look at an alternative cooling solution using piezoelectric fans to cool these LEDs. Now, this work is in conjunction with Siemens, where they're looking at exploring different types of active cooling solutions for LEDs. Now, typically LEDs these days are passively cooled. They'll just have a heatsink on there. These things will kind of look like your, the heatsink, the big bulky heatsinks in your computer, computer. And so, if you can actually reduce the temperature of the LED using some sort of active solution, whether it's a standard sort of rotating fan or some other sort of cooling solution, you can really increase the longevity of these fans. Now, these are sort of our project objectives. We've been given a standard geometry, which is about a 50 by 60 millimeter area and about a 30 millimeter height. And we're looking to design heat sinks around this piezoelectric fan, which is this fan right here. So this piezoelectric fan works when you have a piezoelectric beam here, and you apply an alternating current. So these things can vary from different voltages, but typically they'll build these things at about 115 volt, 60 hertz, so that you can plug these into the wall. And because the beam's resonant frequency is built to your input signal, the beam resonates, and you end up having this huge displacement up to about an inch or so of this beam, and you have this sort of flapping cooling action, which I'll show in a video that comes up. Now, one of the things is we've been told that there's about 20 watts of heat from an LED that we're trying to cool, and we're trying to reduce the surface temperature on the back of the system from about 100 degrees down to about 60 or 70 degrees. The other requirements are sort of long-term stability, so more than 20,000 hours without mechanical failure, and very low noise. And noise is probably one of the main drivers of this. And with piezoelectric fans, running at 60 hertz, you really don't hear any noise. We're able to be able to run a fan, unlike your typical computer fan, where you sort of hear these things kick in at a very low noise. So as we go forward, we started looking at how we can take this sort of piezoelectric fan, this sort of flapping beam, and place it on this heated block, which is our sort of LED block. We started by looking at the different orientations we can place this. There's this what we call forward, vertical, parallel to it, and horizontal orientation. And what we did was we took some of these fans, and I didn't mention that you can buy these piezoelectric fans now sort of off the shelf from various different vendors. And we built a setup where we tried to simulate. So this black box block here is our simulated heatsink, where we input about 10 watts of power, and we heat it up to about 100 degrees Celsius. We embed it with all these thermocouples to monitor the temperatures of that. And we have this fan, which is here. shows a little better here. And we sort of move it around using an automated system to try to determine sort of the optimal positioning, location, placement, relative to this heated block. And we try to measure in terms of a convective cooling coefficient to see its cooling efficiency. So this is sort of our first order approach to looking at optimized orientation. What you see here is this from a side view of this piezoelectric fan here, and as it turns on, you see it flapping. And again, this is about 3 inches long, and so you have this sort of flapping, which is upwards about an inch or so. And we sort of move it around relative to the block, and we monitor the temperatures. We do the calculations. This video is a little pixelated, but I think you should still be able to see this fan and the block. So then from there, we tried all these different configurations, and the primary things are, distance of the fan from the heated block, how much coverage the fan takes up, and of course the different orientations. So on this graph, what you see here is this convective coefficient value, and for those of you who aren't familiar with heat transfer, you want the higher the better. You want a higher convective coefficient as possible. And typically, free convection, where it's just air, still air, maybe moving a little, it has a value of about 5 to 20 watts per meter squared Kelvin. And in this graph here, we have the convective coefficient and the percentage of the plate covered by this piezo fan. So these two lines represent both the vertical configuration in this position and the horizontal configuration there. And we sort of just scanned it around. And what we found is that you end up getting the highest convective coefficient and the most cooling when you have about 12.5 to 25% coverage of that plate. And I'll talk about why in a bit. In the case of vertical and horizontal configuration, the vertical configuration gives us a higher cooling effect than this horizontal coefficient. And it sort of intuitively makes sense considering, if you think about this sort of flapping scenario, you are sort of getting a bit of a symmetric cooling relative, in these two directions. And so, in the case of a horizontal scenario, you're not taking advantage of some of the cooling that's occurring above the fan. This is the same similar thing with the convective coefficient, and in this case, this is distance from this plate, from this block. And what we found is that you want to stay as close to the block as possible, but actually, the forward configuration gives you the most cooling relative to these other two configurations. However, one of the issues with working with a configuration like this is, mounting this thing and building something to sort of hold it on there. This vertical orientation seems to have a more, or is better to design around, especially within our constraints, our physical constraints, where we want to limit the package to about 30 millimeters in height. So then, in order to really understand this piezoelectric fan, we wanted to look at using particle image velocimetry to visualize what's going on near the fan tip and further down the line, and sort of what this the flapping of this piezoelectric fan produces. So in this, we took this over to a lab in Hesse, where they have this particle image velocimeter. Essentially, there's a laser with a camera orthogonal to that, and over here you see this piezo fan in this container, in this chamber. And this chamber is filled with atomized oil, and the laser basically syncs up with the camera to allow us to visualize snapshots. It takes 2 images consecutively, and then based on the 2 images, what you see, so in this case, you see 2 images here, where this is the fan, and this is sort of the overseeded atomized oil. You can then calculate these velocity vectors from that. So you take the data, you process it, and this is an image here where this is from the side, a piezo fan, and these little, and the colors represent the flow velocity and the velocity vectors here in these tiny arrows. What we're seeing from a lot of these images is that there's this sort of V that comes off the fan as it sort of spits off these little vortices coming off. And this angle varies from around 45 to 50 degrees relative to the center line. And this sort of makes sense. If we go back to earlier where we're talking about this coverage at 25% or 12.5%, in a vertical orientation, you can imagine this block around here. So when the air sort of spits off at this angle, at 25%, you end up getting most of the air actually hitting the surface that's heated. When you're too far down here, you end up not getting enough cooling. When you're too far back here at full coverage, a lot of the cooling, the high velocity, isn't touching the surface. We were able to confirm this again using a hot wire anemometer, where we had this fan. This is the top view now. It's also a top view or side view. And we basically took bulk flow velocity measurements along in this sort of grid matrix. And again, the higher, I guess the red means a higher flow velocity, and blue means it's cool. So in this case, you see the highest flow velocity are near the tip. So this is more of a bulk flow, whereas in the previous image, it's more of an instantaneous snapshot. And what we see here is that there's this angle here again, which confirms our data. So then, we took this and we decided we want to take advantage of this and try to redirect the flow and contain it to cover our heated area and try to maximize the cooling we can get. One of the, this might have fit a little better earlier in the slide, but one of the things we wanted to look at also was looking at simulation, how we can take that simulated data. Unfortunately, with 2D simulation, while you can get some of these nice images without these artifacts of the flow profile through different heat sinks and structures, it's very limiting. It's very computationally intensive. So we actually began iterating certain heat sink designs and looking at actually measuring them experimentally. So this is sort of where we are now. Again, in this graph, we have the convective coefficient, and these various points are measured values off a couple designs we've iterated through, thinking of ways we can sort of focus the flow on the heated surface itself and not losing it off to the side or off to the top. So around here, this is just a heated block with free convection. You get a value around 20, 25 watts per meter squared Kelvin. We looked at some designs where there was a channel involved, and we put in a little airfoil to see if we can sort of redirect that flow around there near the tip of the fan. And in this case, there's no fan down here. This is what we showed earlier in the vertical or in the horizontal or the forward configuration. You get values around 65 watts per meter squared Kelvin. With a heat sink, these heat sinks sort of look like your standard sort of fin sinks, and the fan straight against it, you actually get some improvement in there. However, we noticed that most of the flow was going along the sides of these channels with not much flow going down. So while you're constraining the flow that was leaving the plate, you weren't getting anything towards the center. So then we added a lid on top of that because we noticed a lot of flow coming normal, moving normal to the plate. And by doing that, we were able to further increase that flow and increase the convective coefficient to about 85 watts per meter squared Kelvin. So this is where we're at. we're continuing our design iterations, looking at different designs, and trying to take advantage of the flow profile that we know now. We'd like to evaluate the flow profile in our different designs and heat sinks, and then continue doing some of this flow visualization work. And then, finally, we're experimenting with different designs, using maybe multiple fans to maybe even increase that cooling coefficient. And finally, there's a lot of local turbulence near the tip. However, much of the flow is laminar. A turbulent flow really allows us to increase the cooling effects. So we want to look at maybe ways of taking advantage of some of these vortices near the tip and creating some local turbulence around there. So with that, open any questions.
Okay, thank you, Alic. Well, I think we can take a couple of questions if there are any. Okay, I don't think so. Oh, we do have one, Charlie.
I was just wondering, did you look at the effect on the efficiency in lumens per watt, total wattage of the fixture? I was just curious, is part of the reason here to improve the efficiency, or is it mainly the longevity of the fixture?
Well, I guess ideally both. But at this point, we haven't quite explored that. We're mainly looking more from the sort of heat side of things and not as much from the LED. But that is something we want to explore. And we can take these convective coefficient values and try to convert that and try to do some calculations on the cooling, or on the effect on the lumens per watt. But that's a very good point.